All right, let's go ahead and start working through this. So we've got hydrochloric acid as a gas, so hydrogen chloride gas, reacting to make H2 gas and chlorine gas. We can start by balancing. We know how to do that at least, right? Got to make sure we have the same number of atoms on both sides. We only have one hydrogen here and two hydrogens there. So we know what we got to do, right? At the very least, we have to do that if we're lucky, which we are in this case. That takes care of everything. Two hydrogens, two chlorines on each side, right? So this reaction or this problem says for the initial concentrations, calculate equilibrium concentrations of each species. So we have a couple things changing. We have every time the HCl reacts, we're going to make a little bit of chlorine and make a little bit of hydrogen, and we're going to lose some HCl, right? So anytime we have multiple concentrations or multiple numbers of moles changing at the same time with a balanced reaction, what's a tool we can use to keep track of everything at the same time? That's our ICE table, right? ICE stands for initial, change, and end, or equilibrium, either way. So before we do anything else, before we worry about the equilibrium constant aspect, we can start to fill this out, right? We have all the information for the initial row. We can put in 0.0575 moles per liter. And here we start with 0 and 0. How do we fill out the change row? We want to do X's, right? But we only want to use one variable for all of these changes. So that was part of why we balanced at the top, right? So we can use the same variable. We know anything we're losing is going to be a minus. And then if the reaction happens one time, we lose 2 HCl, right? So if the reaction happens X times, we're using 2X HCl. So it'll be minus 2X. On our product side, plus X and plus X. So you guys didn't forget everything. Okay. You just blocked it out. Okay, so now that gives us an algebra expression for each of these, 0.75 minus 2X. At the end of the reaction, it's just what we started with and plus the change, right? So X. So now the question is, how do we solve for X? What's the first rule of equilibrium? Go ahead. You're ahead of me. What's the first rule of equilibrium, right? Products over reactants. So we have this value for K, 4.2, 10 to the minus 34 equals concentration of hydrogen, concentration of chlorine over concentration of HCl squared. Why do we square it? Because of the coefficient. Remember, each of these in our products over reactants, in our equilibrium expression, everything is raised to the power of its coefficient in the balanced reaction.
So, can you explain like the logic behind why we square that's the coefficient of 2, or cube if it's a coefficient of 3?
Not without getting into kinetics in more detail. Yes, you can mathematically. It winds up coming out due to the way that we need these things to run into each other. You have to have these two things run into each other for the reaction to happen, which means the probability of that reaction happening is based on the concentration times the concentration, because you need the two things to hit each other, which means that probability is going to be squared. It gets more complicated than that, but since this class doesn't get into rates of reaction, it's kind of hard to actually show the math for it. It's kind of a take me at my word for now and take more chemistry, right? Like we were talking about. Yes, take more chemistry. Give in to the dark side. All right, so then how do we solve this? Well, we just plug in our expressions we just came up with, right? In here. So we're going to plug in X for hydrogen concentration, X for chlorine concentration, and 0.75 minus 2X for HCl concentration. So X times X over 0.75 minus 2X squared equals 4.2, 10 to the minus 34. Now we just have to solve for X, right? Which, if you've got a solver, you can type it in just like that. That's good enough. The problem is, one of the things that you might run into, there's a couple cases that we'll see in this class where a solver actually won't be able to solve what we give it. When X gets really, really big or really, really small, sometimes those solvers have to make approximations when they're solving. And when they do that, sometimes you're going to wind up with just X equals 0 if you try to use a solver, or it'll just give you an overflow error sometimes, where it can't carry enough decimal places. It's less of a problem now that computing power is a lot stronger than it used to be, but I think even last year we wound up with a couple examples where if you plugged it as written into a solver, it gave you an error. So we're going to have to do our approximation. When we have a really, really small X, what can we assume about X? Or sorry, really, really small K, what can we assume about X? It's also going to be really, really small, right? So if X is approximately 0, we can turn this 0.75 minus 2X into just 0.75. If X is really small, then our final concentration of HCl is going to be really close to 0.75.
We still have to square that.
We would still have to square it, yeah. So, but we wind up with something that's a lot easier to solve because we don't have to FOIL anything. We're just going to get X squared over 0.75 squared. Solving that for X isn't so bad, right? So 0.75 squared is going to be something pretty close to 0.5. 3.5 plus, yeah, pretty close to 0.5. So it should get something pretty close to 2. No problem. 0.2 times 10 to the minus 34, then we're going to square root that. So we're going to get something like 1.5 10 to the minus 17. For X. Really? I didn't expect to be that close.
1.53, or I guess with sig figs.
With sig figs 1.5. Sometimes all of those rounding approximations you make in your head doing mental arithmetic, they all cancel out and you wind up with close to the right answer. So we're going to do an example in the next slide, but there's a way around it. But basically when K is not really, really big, or when K is not really, really small, we can't make that assumption, right? In which case, then you have to use a solver. But the good news is, or a quadratic equation. The good news is that if K is a medium number, like, you know, call it 200 or something like that, then you're not going to run into the solvers having problems with it. Brody?
If we assume X equals 0, why would we use a single numerator instead of two denominators?
Because then we wind up with something that doesn't make sense. We just get X equals, we get 0 equals this.
So if you want to call it, so it's always on the denominator.
It's always going to be in the difference. If we can assume that X is really small, then the difference is pretty close to what you started with. When X is by itself, we're not going to make that assumption for that. Otherwise, you just wind up with something that's close to true, but not exactly true, like 0 equals a K.
Wait, so if I kept the X in the equation, would that like result in getting a positive and negative one?
Yes, and you probably, if you do plug it into a solver, you're probably gonna get more than one answer, because just like for a parabola has more than one root, right? When you use quadratic equation, you get a plus and a minus. But if you get two answers out of a solver, only one of them will make sense. The other one actually won't be physically possible. You'll either get a negative concentration or you'll wind up with more than it's possible to make. Like you can't have X be bigger than 0.375, right? Or else you get a negative concentration and that can't happen. Right, so that sometimes you see issues like that. You kind of have to have at least one or the other, right? So I could give you the equilibrium concentrations and ask you to figure out what K is, right? But at some level, you have to have enough pieces of information to be able to solve something like this. All right, any other questions on this one? Does this answer our final question for the problem? More or less, we're right there. It says calculate the equilibrium concentration of each species. Well, solving for X gets us two of our concentrations, right? And then we just plug in X here to get our last concentration. But this is where we also show that our assumption is valid. X is less than 5% of what we started with. In fact, X is so small that within sig figs, this number is not even going to change, right? If X is 10 to the minus 17, then really we don't have 0.75 anymore. We have 0.749999999999 something. Really close to 0.75. So that's what we were talking about before. If you assume this is 0.2, if you let this be 0.2, then you can't solve for it. You have to leave an X in there somewhere. And so we always make the difference. Anytime you have something like this where you have minus X or a plus X, if you're going to assume X is really small, that's where we make the assumption so that that can go away. Then take the square root of it. So 0.75 squared is about 0.5. So if you take that times both and then times both sides by that, that's like dividing by 2. That's probably why that happened. All right, any more questions on this one? Is this seeming familiar? Back close to back where we were? Doesn't take that long. You haven't been away that long. So let's put a new spin on it. Same reaction, except we start with a bunch of hydrogen and chlorine and no HCl. How is that going to change things? We could think of it that way because the reaction is going to happen backwards, right? So it's a little bit weird to say we're starting with products and we're going to make reactants. We're not used to thinking about it that way, but we could. The thing is, if we switch products and reactants, that's going to mess with this number, right? Because if we rewrite it so that it was H2 and Cl2 are on the left-hand side, then our products of a reactants is not the same as it was, which means our number is going to be backwards. So we can just leave it the way it is, though, and we can still fill in the ice table. We're just going to have 0 on the product side, and we're going to start with 0.40 and 0.40 on the reactant side. How is that going to change the change row? Max?
It would still be 2x.
It would still be 2x, but it's going to be plus 2x. we have a bit of a problem here. This is another one where using a solver, you could plug this into a solver at this point. Throw everything in here, solve for x. The problem is, can we assume x is really close to 0 in this case? Why not? Why were we able to assume x was close to 0 the other time, last time? Because k was so small, right? Almost all of it was going to stay as reactant, right? In this case, we start with a whole bunch of product. So is it going to stay as product? It's going to do what? It's going to go that way. Almost all of our product is going to turn back into being reactant. So we can't assume x is going to be really small because the opposite's true. X is going to be big because almost all of this is going to react to form reactant. So if we just plug this in, we plug this into Wolfram alpha. I think this is going to be one of the ones that'll actually give you an error too. Because you wind up with x being too close to 0.40 for it to work. So 4.2 e to the minus 34 equals 0.4 minus x squared over x, or 2x squared. And numblocks got me again. Solve for x. That's the right equation, right? That looks right. And we get our two possible solutions are both x equals 0.4. And it doesn't even give the option to show more sig figs. Maybe it does if I hover. No, that just searches for 0.4. So in this case, that doesn't really help us because if x is 0.4, what are we going to get? We're going to get 0 and 0. And over here, we'll get 0.8, right? That's a decent first approximation, except that we know from equilibrium, we can't have everything equal 0. Can't have anything equal 0 in the equilibrium expression, right? There has to be some amount of everything. So we need more sig figs, and our solver is not giving us the option. So how do we get a number then? Basically, we do it again. We say, okay, our first approximation is that x is 0.4. Basically, you let all of it react backwards, and then you have the same reaction that we started with at the beginning. Right? If x is 0.4, then we wind up, after the first step, we wind up with this being 0, this being 0, and this is 0.80, right? That looks a lot like the problem we did one slide ago, doesn't it? So we basically just do the same thing again, and now we can assume x is close to 0 again. You basically let it all react backward, and then let it react forward again. And that's not how nature actually behaves. It's not like it goes like, but you can kind of think of it like a pendulum. It's going to swing all the way to the left, and then it's going to come back towards the right to reach equilibrium. And we can calculate that. When we have a really small k, we want to start with all of it as reactant. And so it's going to react just a little bit forward. If we have a really small k and we start with everything as reactant, all of our calculations are just going to say it goes all the way to the reactant side. Right, so sometimes you just have to do it. If you wind up trying to solve for this, or you either get something that you can't solve because you can't make the x is 0 approximation, or your solver gives you something where you still get a 0, we don't want that. You basically do it twice. Let it all react toward the other end, and then we can fill it in and say, okay, well, 0.80 minus 2x and x again, basically a second ice table. This is kind of a trickier way to think about it, but this is one of the cases where you can't make the assumption that x is small, but what you can do is assume it reacts all the way one direction and then try it again. And then we'll get x squared over 0.80 minus 2x squared. Assume x is 0. Lila? Now, because we're starting from all reactants, now we can assume x is small again. We can't make the assumption that x is 0 here because we actually know the opposite is true. X is going to be really close to 0.4. Parker?
When you plug and solve, do you plug it the opposite way? Since you switched it backwards, and then solve, you go reverse, or you reverse it back, then plug and solve, you can plug and solve with reverse. If that makes sense.
Either way, if I'm understanding what you're saying. So once you go, and really you can think about it like doing 2 ice tables in a row, right? So here was what we got after the first. After the first round, where it gives us x is 0.4, we got this, but we can't leave it as 0. So now we're just going to basically say, okay, well, now I'm going to do an ice table starting from here. And then we can do minus 2x and plus x and plus x. And it looks just like our first example. Okay. All right, that's one of the less important types of problems, basically, because you only run into this if you have a weird case like we just did. If K is really, really big and you're starting with the reactants, you assume it reacts all the way towards the products and then calculate X, and then you can make the X's small assumption again. Lisa?
I think I might have just missed it, but why do you do second ice table? Like, what's the purpose of it?
Because we know that at equilibrium, nothing has a concentration of 0. Right? We know we have to have some small amount of these. It's going to be really small though, which is why just plugging into the solver gave us 0 for an answer, right? Gave us 0.4 as our X. We know that we can't actually have that though. So basically we're kind of doing the calculation, getting closer each time we do it. We're kind of approaching the correct answer asymptotically, if you want to think about it like that. This is a decent first approximation because it is going to be really close to 0, but it's not going to be, we can get more sig figs than just 0. So that we do it again and we get closer to the real answer. What's called an iterative process. Sometimes when you do things multiple times in a row, you get closer each time. Incidentally, that's also how we have supercomputers solve quantum mechanics equations. Is basically they make approximations that aren't exactly true, but they get close to the real answer. And then you have it take the answer from the first time and plug it back into the equations and do it again. And it gets even closer and closer and closer. So you have it go in circles basically until you get the same answer twice in a row within sig figs.
So how does quantum computers work then?
That's a whole different thing. We can use traditional binary computers to solve quantum mechanics equations like Schrodinger's equation. But they solve it what's called numerically, meaning it's an approximation. It's not an analytical answer would be if we got an exact answer. We can't do that with real quantum mechanics equations with traditional computers because of the 3-body problem. So we wind up making these approximations and we just have the computers crank through a bunch of different options in a row and get, oh, this one seems like it's the most accurate. Gabby, and then back to you. Because we can't have zero for if we're talking about an equilibrium reaction, you can never have anything. It's nothing. Blah blah blah. You will never have zero as your final concentration for something in an equilibrium process. If it's zero, it's wrong. If it's 0 point something, that's fine. It has to have, you have to have some numbers to it. Like for the last one, when it was 0.75, we got 1.5 times 10 to the minus 17 was our final concentration for these, right? That's a really small number, but it's not zero. It's really close to zero, but it's not zero. Okay, so anytime you get, if it's exactly zero, then it's wrong. 0 point something is okay. Does that make sense? Because when you, if the solver says 0.4 and you plug in that for your x and you get exactly zero, then that can't be the right answer. Then
So I'm still confused on like the products.
so how did we know that this was a minus and this was a plus? Because we know that the reaction has to happen backwards because we have zero reactant here and we have a bunch of product. So we know it has to react that way. Does that make sense? Okay.
Where did the three body problem?
The three body problem comes into play. So who's heard of the three body problem besides the Netflix series? The three body problem basically means if you have more than two things acting on each other simultaneously, we can't actually calculate their attraction towards each other at the same time. So basically we can, if we have just the Earth and the moon, we're talking about gravity and the gravitational force between the Earth and the moon. If we only have the Earth and the moon, we can calculate the attractive force of gravity exactly, analytically. But as soon as we introduce a third thing into the system, like the sun, well, the sun's gravity affects the Earth and the moon, and the Earth's gravity affects the moon and also the sun. We don't have the math. Math doesn't exist to solve that, to actually give an answer when we have three bodies acting on each other at the same time. And the same is true with electrons and nuclei. As soon as you have more than one electron in one nucleus, you can't solve their attraction. You can't solve the orbital energies exactly. Does that make sense?
Yeah. But like if you were to like throw a hydrogen atom in between the moon and the Earth, then like would that screw everything up?
If you carry enough sig figs, yes. So basically the way we get around the three body problem for doing orbital dynamics and things like that for rocket science is we basically just assume that whatever's closest matters more. We basically just say, okay, well, the Earth's gravity matters more to us than the sun's gravity does because we're so close to the Earth. But it's not exactly true. But in your example, I'll put a hydrogen atom in there and even that throws it off. Technically it does, but it's going to be such a small amount we can basically ignore it.
Will AI and supercomputing help with calculations like that?
Supercomputing does. I'm not convinced AI will. Quantum computing might, because the architecture of how you structure programs in a quantum computer is dramatically different than in a traditional computer. Probably not AI, because AI has the same limitations that humans. AI can only know what math we teach it. And since humanity as a species does not understand the math to solve the three body problem, then it doesn't really, and AI is not really going to help unless it gets to the point where it's deriving its own math based on what we give it. And then in theory, maybe, but that's nothing close to the AI that we're seeing right now. Landon? Okay. Yeah, we're getting off topic a little bit again, but
I like on top.
off topic's fun. That's why I don't fight it too hard. All right. This was the last new material we went over. We started talking about gas laws, right? And you guys did this experiment, right? Where you changed the pressure and you looked at how the volume changed. Right, if you decrease the volume, if we take this piston of closed air, we decrease the volume, what's that going to do to the pressure inside? It's going to increase, right? If you decrease the volume, the pressure goes up. We saw something that looked like a 1/x graph with that, right? Where if you keep cutting the volume in half and in half and in half again, the pressure is going to double and double and double again. Right? And the opposite's true as well. If you keep increasing the volume, the pressure is going to decrease. If you double the volume, the pressure will be cut in half. Right? And we extended that to the size of the entire universe, right? If you keep doubling and doubling and doubling, you can't get to an infinite volume. And if you can't get to an infinite volume, that means there's always going to be some small amount of pressure. Which was kind of a fun thought experiment, but what really mattered out of it is we got this relationship. Boyle's law said pressure times volume of any closed system at a set temperature is going to be equal to a constant. Just looking familiar? Ish. Or the more common way to write it is P1 V1 equals P2 V2. So for any closed system of gas at a constant temperature, the pressure times the volume is going to be equal to the same constant. So if you change the volume, the pressure is going to change. We can calculate that. If we know pressure and volume at one point, and then we change the volume, we can calculate what the pressure would be at a new volume. Right? This is what we did with the syringes. All right. So, and then we started talking about pressure and pressure units. The main thing we came away with from all these pressure units is that all of these are equal to each other. They're all on your conversion sheet. And then basically you can combine them in any way you want to convert pressure units. Pressure is almost never going to be more than a one-step conversion, right? Because no matter what pressure units you have, you can find that pressure unit related to 1 atmosphere. Right, so 1 atmosphere was equal to 760 millimeters of mercury, which is equal to 1.01325 bar, which is equal to 101,325 pascals, which is equal to 14.7 psi. All of these different units, they're all related to one standard atmosphere, which again shows our Earth-centeredness. That's the standard atmospheric pressure on Earth. Anybody know what the standard atmospheric pressure is on, I don't know, say Mars? Venus is different. Venus is a lot higher. I don't know if it's that. Is it 12 atmospheres on Venus? Oh, you're just guessing. I think the problem with Venus is also that its atmosphere is made up of extremely corrosive chemicals like sulfuric acid. I want to say it's under 100, I thought, but I could be wrong about that. If you want an interesting read, if you're into astronomy and space exploration, you should read about the Soviet probe that they sent to the surface of Venus that lasted like 3.5 minutes before it was just too irrevocably damaged by the pressure and sulfuric acid. It was pretty interesting. It's almost impossible to explore the surface of Venus because of how nasty the atmosphere is.
Fun fact about that, they like designed it so that it could float because they didn't know if it was like gonna be some like jungle or something.
Yeah, there was a lot of speculation. They really didn't know. I mean, and actually that's, if you want to think about the early astronauts as being really pretty brave explorers, they didn't actually know when they landed on the moon for the first time if their landing craft was going to sink into and be swallowed up like quicksand. So they were really taking a lot of chances. Every time a human has gone into a new space exploration phase, it's been really a pretty big gamble in a lot of ways. I think just to answer my first question, Mars, this pressure on the surface of Mars, I think is about 15% of
Yeah.
of Earth. It's about 0.15 atmospheres, but it's almost entirely CO2. All right. So let's do a practice problem. We've got P1 V1 equals P2 V2. We've got a 750 milliliter bottle is sealed with 760 torr. What is the pressure if the volume expands to 1.75 liters? We take a bottle and we increase the volume. What's P1? Pressure. Do we have a number for it? 760. So we're sealing it at 1 atmosphere. What's V1? 750 milliliters. We've got to know at least 3 of these pieces in order for this to work, right? Or we have a system of equations and we need some more information. So what else do we know? V2 is what? 1.65 liters. Is that are we ready to just plug and chug?
Yes.
Almost. It doesn't matter what volume units you use or what pressure units you use as long as they're the same. So we've got milliliters and liters, so we just got to either convert liters to milliliters or vice versa. Now we're ready. So 760 torr times 0.750 liters equals 1.65 liters times P2. Gets something like, let's see, something like 300 torr. We assume that this was plus or minus 1, then we get to keep 3 sig figs. Since I gave you an ambiguous number in the problem. Didn't mean to do that. We done?
Yes.
Got to convert to PSI. This is our final pressure, but since the problem specifies our units, we just have to do a quick conversion. Got 345 torr. And from our equation sheet, we know that 760 torr is 14.7 PSI. So something like 6. Man, 760 times 0.75, and then divide that by 1.65. What do we get for PS at 6.70? Something like that. 6.67. So this is Boyle's law, is actually when you set it equal and we're talking about a change in pressure or a change in volume and how they're related. And it's what's called a simple gas law. And because basically these simple gas laws, this is all we can really use them for. So we have these 2 variables and we know how they're related, so we can look at a before and after. But there's not a whole lot that's really interesting we can do with that, because all we can do is problems like this. Here's your initial set of conditions, and then something changes. What's your new one? Your new pressure or your new volume? Not really all that interesting. But it's one of a set of about 4 simple laws, simple gas laws. And they all have the same general form to them. They're all going to relate 2 variables to each other. Right, so Charles' law was the next one. Charles' law. Well, the good news is you don't need to remember all of them, and you definitely don't need to know what they're called. Charles' law is the one that relates volume and temperature, right? And this is where we got into, okay, well, it's not strictly proportional because it doesn't hit 0. It doesn't go through the origin, right? So what do we do with our temperature scale to make it so we can write a simple gas law for it? What is it about Celsius that makes it so that this doesn't work, so that it doesn't go through the origin? 0 Celsius is too hot. In order for this to work, we need 0 on our temperature scale to correspond with 0 volume. Right, and that's why we stopped using Celsius and we used what instead? Kelvin, which is what's called absolute temperature. So Celsius was derived from looking at melting point of ice and boiling point of water. Absolute temperature, it's called absolute temperature because it's actually looking at the true value of the kinetic energy of those molecules. Right, so 0 Kelvin is called what? Absolute 0. It's the point where you can't get any colder. Right, so, and if we do that, if we switch this from being Celsius to Kelvin, then 0 Kelvin, we actually can come up with an approximate value for it, or make this equation work. Right, we can't actually get to 0 Kelvin. That's part of how we got derailed the other day, was talking about absolute 0 and if you could or couldn't make it there. So putting all that aside, since we've already discussed that, basically just we know 0 Kelvin is a value that exists even if we can't get there. And if we put our temperature in terms of absolute temperature units, which are Kelvin, there is actually an equivalent to Kelvin for Fahrenheit called Rankine, but nobody really uses that because nobody who does serious calculations uses Fahrenheit because Fahrenheit's garbage. So instead, we pretty much just look at Kelvin. And if we do that, we get an equation that looks really similar, where we can say, okay, well, if we double the temperature in Kelvin, the volume should double. We can follow that up. If you keep doubling the temperature, the volume should keep doubling. Which also means the opposite's true. This is actually kind of something that you may have seen before. If the volume increases, temperature for a set of gas or for a set amount of gas should decrease. Because if you look at this equation, when we actually write out the simple gas law for Charles' law, we're going to wind up with V1 over T1 equals V2 over T2. Basically, if you've ever had a CO2 tank or something that just vented, or a propane tank where you burned propane and you got frost forming on the outside of it, it's because you're letting that gas expand and you're dropping the pressure. And you wind up with, it's a little bit more complicated than just this case because we have pressure changing as well. But it's related to why you get that frost forming on the outside of a propane canister when you burn it for an extended period of time. But basically, this is just going to be the same sort of problems that we asked before. If you have a 1 liter system and you heat it from 22 Celsius to 51 Celsius, what is the new volume? If you know any 3 of these pieces, you can solve the last one. what should happen if you seal a 1 liter system and then you heat it up from 22 Celsius to 51 Celsius? Should the volume go up or down? Volume should also go up. It's not going to double because we need, in order for this to work, we need our temperature to be in Kelvin. So how do we put temperature in Kelvin? Not quite. I'm going to add a set number to it. So if temperature 1 is 22 Celsius, temperature in Kelvin is always going to be equal to temperature in Celsius plus 273.15. You just add 273 to everything to get it to Kelvin. A note about the units here, I'm not going to mark you down if you write degrees Kelvin, but technically that's not accurate. It's not true. So you don't write Kelvin like that. And the reason is because degrees by definition means you start with a set range and then you break it up into a set number of pieces. That's not where Kelvin came from. Celsius comes from, here's our melting point of water, here's our boiling point of water, and I'm just going to break it up into 100 pieces. That's not how we got Kelvin, so we can't call it degrees. And even degrees in degrees rotation is the same thing, right? Here's 1 rotation. I'm going to break it up into 360 even pieces. But it's starting with a set range and breaking it up into chunks, as opposed to just saying 0 is 0. Landon? Okay. So what's T2 then? T2 is 51 Celsius, which is going to make it 324. And then our volume, V1, is 1.0 liters. Plug and chug. So with the rest of these simple gas laws, it doesn't matter what units you're using as long as they're the same. The exception is temperature. Temperature has to be in Kelvin. You've got to, this reaction doesn't work, or sorry, this equation doesn't work if you're in Celsius. Landon? Then you got to put it in Celsius and then go from Celsius to Kelvin. Which is why I started this off by saying Fahrenheit's garbage. We don't want to deal with Fahrenheit because it's one extra conversion you have to deal with before you get it to something useful. All right, questions so far?
Where does 0 Fahrenheit come from?
0 Fahrenheit comes from the coldest temperature that Lord Fahrenheit was able to make, which was a mixture of salt and water. And I believe 100 Fahrenheit was the body temperature of a cow, but that might be an urban legend. That's what I was taught by my chemistry instructor in high school. So that's what I will repeat here. Cow's 101 Fahrenheit. Oh, okay, so that's not true then. There was something else I heard that would make more sense. All right. Awesome. It could have. They just had a measuring error.
Yeah, I mean, that's why we can talk about sig figs.
That's true.
We can prove to know we're now 98.6
Instead of 100. Okay. That makes sense.
I just by placing a thermometer under
And maybe he was running hot, running fever at that point.
But you're right about the mixture of ice and salt.
Yeah, it was basically the coldest liquid mixture he could get easily, given his constraints. Which was, I think, in the 1600s, 1700s, something like that. So they didn't have access to a lot of resources.
Yeah.
All right, we're gonna go through these next ones kind of quickly. So if we start from these two laws, these are the first two that were discovered, were really published. They didn't want to do this experiment with the fixed pressure. Why not? What happens if you, or with a fixed volume? You do a constant volume, we seal it and then we heat it up, what happens? It breaks, pops, explodes, depending on how large and what materials you're using, right? So they, instead of doing this next one experimentally, they did it from classical geometry, from Euclid's axioms. You can come up with, if A equals B and B equals C, then A equals C. That's the, what, transitive property? I don't remember all those names. Something like that. Transitive might be A plus B equals B plus A, but I don't remember. No, that's commutative, huh? Anyway, we can say the same thing about proportionality. If A is proportional to B and B is proportional to C, then A is proportional to C. Remember, proportional was that term that just meant that this that the slope of the line is linear and it goes through zero, goes through the origin. This allowed us to then get, okay, well, if volume is proportional to temperature and pressure is proportional to 1 over volume, we can get almost the same equation, except with pressure instead of volume. P1 over T1 equals P2 over T2. You guys see how these are all basically different ways of saying the same thing? Like the types of problems I can ask you, as long as you can recognize what the variable is, oh, that's a volume unit, then you can figure out which of these equations to use, right? And I'm not going to test you on what they're called, because that's more historical than it is really relevant to actually solving these things, right? You don't need to know that this is Charles' law to be able to plug stuff in and solve. And then there's one more way we can look at this, which is basically taking all of these and combining them into one combined gas law, which is still considered a simple gas law. But if we can do the same sort of substitutions we were doing before, and we can get P1 V1 over T1 equals P2 V2 over T2. Just taking these three and combining them together. So this one's just called the combined gas law. We're still assuming one variable is held constant though. So if we're keeping, what's one other thing that could change, that could affect the pressure besides volume and temperature? Force, yeah. And pressure, so pressure is equal to force over area, right? Changing the volume affects the pressure because you change the area. Changing the temperature changes the pressure because you change the force here, right? Because you made every gas molecule hit harder if you increase the temperature. What else could change the total force? How many total impacts you have, right? If I throw a ping pong ball at the door versus a bowling ball at the door, that's two different forces, right? But if I throw 1,000 ping pong balls at the door, that might be equal to the force of the bowling ball hitting the door. Maybe. Wind resistance winds up playing a role in it, right? But it's kind of like the what's heavier, 1 pound of feathers or 1 pound of bricks. They're the same, right? So if we increase the number of impacts, we can increase the force as well, which is another way of saying increase the number of molecules. So even this combined gas law is not everything, because we're still assuming this right here, constant number of molecules. So what would happen to the force if we doubled the number of molecules? we would assume that the force would also double, right? We have twice as many impacts. Every impact is the same force as it was before, but we have twice as many of them. If I hit the door twice with the bowling ball, that's twice as much force than as just hitting with the bowling ball once, right? So that allows us, so our last variable is moles. We represent moles with lowercase n. There's one more. This is the last one. This one actually has a familiar name. This is Avogadro's law.
Oh,
my God.
It's the same guy. So Avogadro's number comes from the same Avogadro who came up with Avogadro's law, because he was talking about how many molecules there were. Right, so Avogadro was the one who took these ideas and said, well, let's extend it one further. If I double the number of molecules, pressure should also double. Which means this is our true gas law. Our true gas law is all four of these variables combined together. And as long as any one variable is held constant, we only really need one simple gas law. Landon? Equals P2, P2?
and you said you needed 3 of those, right? So how many variables?
Well, so now we've got a total of 8, right? So if we're dealing with a change like before, we need 7 out of the 8 in order to solve it, right? Or we would need another equation we could substitute in. So it's no harder mathematically, because I got to give you more information. You just got to know how to deal with the units and what goes where. So here's the good news about this equation, this combined form of all of them, is anything that's being held constant is the same on both sides, right? So let's say it's a constant number of moles, then N1 is equal to N2, right? Which means when you try to do any sort of solving, they just cancel out. Let's say N was 1.5. If it's the same before and after, we just have the same number on both sides of the equation. It just disappears, right? Anything that's constant on both sides of this equation, before and after, just goes away. So if moles is constant, then N disappears from the equation. If pressure is constant, then P disappears from the equation.
But moles are proportional to volume, so what does that mean for volume?
So if you double the number of moles and pressure is constant, then the volume should double. Right, so all those different changes we're looking at changing one variable and how it affects one other variable. We're assuming the other ones are staying constant when we do that. So we said doubling the number of moles doubled the pressure at a constant volume. Or if we hold the pressure constant, doubling the number of moles doubles the volume and the pressure doesn't change. Basically anything, this is your one ring to rule them all. This is the only simple gas law you need. Because anything that's constant, you just erase it from both sides. Right, and so this is the form that's on your equation sheet. I don't give you Boyle's law and Charles' law and Avogadro's law and the combined. I just give you this because this is all of them put together. Landon? If your pressure and your volume don't change, then nothing changed. Actually, that's not true. If neither your pressure nor your volume changed, these go away and you get 1 over N1 T1 equals 1 over N2 T2. So your moles could change and your temperature could change. And they're inversely related. So this is actually why when you vent gas out of a cylinder, why frost forms on the outside, because you're dropping the number of moles inside that container. If you drop the number of moles inside that container, the temperature goes down. Right? All of these things are changing at once. And in that case, though, because your volume is increasing, your moles is decreasing, depending on how you define your system. Lisa?
So to each law, like what are the variables is constant?
Yeah, and if you go back and look at the slides, you might notice that usually I was pretty careful to say that something was staying constant. Like a sealed 2-liter bottle is left in a car and reaches this temperature, but the volume is given to you, but the volume is not changing. So in that case, it's sealed, so N is constant before and after, right? Which means you can cancel it out. And if the volume is not changing, volume cancels out. So you just get P1 over T1 equals P2 over T2. So basically anything that's not changing, just erase it. And then this is the only version you need to know. All right, with 10 minutes left. There's one more corollary to this. It's the same equation represented a little differently. This is what's called the ideal gas law. So if we know this is true, these are all the variables we need to describe a gas. These are all the things that can change your pressure, are either moles of gas, temperature of the gas, and the volume of the gas. Which means that this is actually true, not just for one case, not just as long as one variable is held constant. This is actually true for all gases. Basically, if you take this, the pressure of a gas times the volume of the gas and divide by temperature in moles, you always get the same constant for any system of gases. This is actually one of those fundamental constants that Einstein was trying to include into his theory of everything, where and it's basically, it has its own name called the ideal gas constant. The ideal gas constant is anytime you have a gas where you can measure these 4 variables, they always give you the same ratio. The pressure times the volume over the temperature in Kelvin over the moles will always give you the same number that we call R. So the ideal gas constant is equal to 0.08206 liters times atmospheres per mole Kelvin. Basically, so for any gas, if you take the pressure of that gas in atmospheres times the volume of that gas in liters and divide by the temperature in Kelvin and divide by the number of moles, you get the same number. Which seems a little bit weird, right? Turns out that this is kind of like the speed of light. This is one of those fundamental constants of the universe and how universe and probability in our universe works. It's a little bit weird to think about the fact that different universes might have different laws of probability, but it's true. In our universe, the way matter and probability behaves means that you always get the same R value. Right, and it comes basically from just the probability of these molecules running into each other and how they occupy space. Landon? I don't actually know why they picked R, capital R, that it hadn't been used before, I guess. And they just went with it. It could be ratio. Ratio would make sense. Where this is useful is that it also means that in addition to this combined form of all the simple gas laws, the ideal gas law basically just takes this and just makes it so it's not a fraction. Multiply both sides by n and t, and you get pressure times volume is equal to moles times R times temperature in Kelvin for any gas. You look skeptical, Max.
No, it's just like, wow.
It is. The other nice thing about this, maybe it's nice from my point of view, is the number one way that I can ask you a question about this that ties into other stuff we've been studying is, this is just one more way that you can get to moles for a stoichiometry problem. If we have a reaction where your reactant is a gas, I'll give you a pressure and a volume and a temperature, and you can get to moles from that. So it's just one more tool in the toolbox to get to how many moles do I have, so I can do stoichiometry with it. And that's what your assignment tomorrow is going to have you do. It's a bunch of ice tables, but with gases this time. Right? You guys should getting so good at stoichiometry and ice tables, you should be dreaming about them. Right? You should be praying that your final is nothing but stoichiometry. All right. That's all for today. I'll post this tomorrow. Comms will have some copies for you, but I'll post it on Canvas as well. All right.
Gabrielle.
I just realized.
I do.
You guys are-
Good.